going to look at inverse proportion, and we've got a question here which is sort of like a real world problem. 12 people are needed to harvest a crop in 2 hours. How long would it take 4 people? Well, let's say we've got an imaginary crop, okay? Here it is, there's our crop, right? The field that big. And what we're going to do is we're going to divide this up into 12 sections. Imagine these are all equal in size. So that is one person working on their section. So you've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people working on this crop. And so therefore the time that one person is going to take, okay, to do this crop is 2 hours for that person. And we can see how long in man hours this is all going to take. But there's much simpler ways to think of this as an inverse proportion problem. So what we've got here, okay, we've got the time taken will be inversely proportional. Now what that means is if something is inversely proportional, it's proportional to 1 over the thing. So we're going to look at the number of people who are going to harvest, because we're going to divide by the number of people. Now we're going to make this into an equation, okay, we can say call our size of our crop K, okay, and K divided by N will give us our time. So we have an inverse proportion problem here. Now we know when the time is 2 hours, it takes 12 people to harvest that crop in 2 hours. So we can find out what our K is by rearranging. And now we've got an equation. So we have an equation where T will equal K, 24, divided by N. And we've got 4 people in this case. So T, when there's 4 people, will be 24 divided by 4. Therefore, that will equal 6 hours. So it takes 6 hours for our 4 people to harvest this crop. Now obviously this is a model, okay, we've assumed that people don't get in each other's way if you employ more people, okay, and that all the people can work at the same rate and there are no allowances for breaks or anything like that. So here we have an example of a mathematical model where we've actually got some limitations and constraints, and yet we've actually managed to come up with a reasonable answer to the problem. Now I just want to look at what the graph of an inverse proportion problem looks at. Now remember, in my previous video I said proportion is, if we've got y is proportional to x, then y is equal to a multiple of x. Now if it's inverse proportion, then y is equal to a multiple, this k value here, of 1 over x. Or we could quite simply just say y is equal to kx. Now if I want to change my value k, we can see this is what happens to my graph. So when it's negative, it ends up over there. When k is positive, okay, we get this shaped graph. So this is the sort of shape of graph we'll get with an inverse proportion problem. And you notice both these equations are exactly the same. Look, you see the green dots overlaying the red dots. The green dots is this equation, the red dots is equation. You can write it either way, so most often we'll use this, even though I like for you to think about it as y equals a multiple of 1 over x rather than just simply k over x. Okay, so y is inversely proportional to x means that y equals k over x. So let's use all that we've learnt to try and solve this problem. When some gas is trapped and compressed, its volume, V litres, is inversely proportional to the pressure P millibars applied. How can you tell from the table that V is inversely proportional? Now there's an interesting thing, because if we know that P is inversely proportional, therefore equals k divided by v, then we can also see that p times v will equal k. So no matter what our p and v values, when you multiply them together, they always equal the same value k. So let's do 1000 times 4.8. That will give us 4,800. If you now do 1,200 times 4.0, we also get 4,800. And if we do 1,600 times 3.0, we also get, funny enough, 4,800. And now 3,000 times 1.6 equals 4,800. We can see therefore that it's inversely proportional. As P and V multiply to get the same value. Okay, So we can easily now see what the equation is going to be connecting v and p. So we know if p equals k over v, well we found our k, because k will equal p times v. So p will equal 4,800 over v. We can now use this equation to solve these two problems. So we want to find v when p is 15. So we know that 15 equals 4,800. And we got v over that, so let's rearrange it. So v will equal 4,800 divided by 15. So we can do 15 into, no, we say we haven't got a calculator, I'm going to try and do this in our heads. So 15 into 48 will go 3 times with 3 left over. So that leaves 300. Now 15 into 30 is 2. So it's going to be 300 is going to be therefore 20. So 320 is the value of v. And this should be a little bit easier because we don't have to rearrange the equation at all. We've got p is equal to 4,800 over 0.96. Now, if we haven't got our calculators and we've got a non-calculator, how are we going to do this? Well, what I suggest is we resort to fractions. Fractions are much easier to deal with than decimals. So we want to divide by 0.96. So that's the same as dividing by 96 over 100. What you should be able to see is you can cancel this down to 48 over 50. And that gives us much nicer numbers. So you've got 4,800. Now when you divide, we turn the fraction upside down and we times. And we can see we can cancel out the 48 to leave us 100 times 50. So our answer is equal to 5,000. So, tip from this question is to remember is actually if you've got an inverse proportion, you can quickly check because all the two values when times together will always give you the same value. Okay, and that's quite an important thing to remember for inverse proportion.